All right, we're going to do the uh, test review for logarithms. First, going to start with the problems that test to see if you know the properties. So calculators won't help you here, and this is a no calculator section. So what you want to do is figure out for each of these numbers, how can you rewrite them using the given values. So whether it's multiplying, dividing, or exponents, how can you rewrite the number that they give you using those three numbers? So for instance, here, log 10, 10 can be rewritten as 2 times 5. So you can rewrite that as 2 times 5. And then using the properties, we know if we're multiplying anything together with exponents, you end up adding the two exponents. So this will equal the log of 2 plus the log of 5. And then we just look to see what those each equal. Log of 2 here equals f, and then log of 5 equals h. So the answer will just be f plus h. And just do the same process for each of these. Sometimes they're a little more tricky, but looks like at least at the beginning here, they're pretty straightforward. So the next one has 3 and 2, which we already have, so we just can go straight to rewriting this. Now when you're dividing, kind of like when you're multiplying, we end up adding. Well, when you're dividing, you end up subtracting. So this will be log of 3 minus log of 2. And the top number is always first, the bottom number is always second. And log of 3 equals g, and log of 2 is f, so the answer is just g minus f. On number 3, we have 25. So 2 and 3 multiplying, dividing won't help you get to 25, but you can rewrite 25 using an exponent. That's 5 to the second power. So 5 to the second power. And then the property here is when you raise a power to a power, it's like multiplying them. So this is going to equal 2 times the log of 5. And the log of 5 equals h. So this is going to equal 2 times h. So those are your three possibilities. Rewrite it using an exponent. Rewrite, well, this one was already division, or rewrite it as multiplication, and then you can use any of the properties that work. It is also possible to use more than one property, so like 1.2, we can rewrite that as, that'd be 1 and 2 over 10, right, 2/10, which is the same as 1 and 1/5. And if you make that a mixed number, or from a mixed number to improper, that's going to be 5 times 1 plus 1, which is 6 over 5. So a little bit of work here. And now you can see, well, we have a 5 on the bottom, so that's good. So how can we rewrite 6? Well, 6 is going to be 2 times 3. So we actually have to use two properties here. Right, this is going to equal 2 times 3, and that'll be over 5. So we'll have the multiplying property on top with the division on the bottom. So this will equal, clear all this out, right, rewrite this over here. That's okay. 22 times 3 over 4. It's out of the way. So this will equal log of 2 times 3 over 5. I'll do the division property first, so it's going to be the log of 2 times 3 minus the log of 5. 2 times 3 goes first because that's on top, even though it's more than one number, just put them together. And the 5 goes second because it's on the bottom. But then the 2 times 3 we can rewrite using this property like we did number 1. Like 2 times 5 was log of 2 plus log of 5. So 2 times 3 will be log of 2 plus log of 3. So we end up with log of 2, which is f, log of 3, which is g, and then log of 5, which is h. So we have f plus g minus h. There we go. For number 5, square root of 2. Here you have to recall that radicals can be rewritten as exponents. So a square root is the same as what power? And so we'll have log of 2, and the same thing as a square root is to the half power. So in this case, we'll kind of do like we did in number 3 and take an exponent and make it a coefficient. So I'm going to take this exponent. It's going to be 1/2 times log of 2. And we know log of 2 equals f. So this is going to be 1/2 f, or you can rewrite that as f over 2. Same thing. And to finish up here, we have log of 30. So we can rewrite 30 by using these numbers. Let's see here. 30 is going to be, let's see, 6 times 5. Start there. That's 30. But then 6 you can rewrite as 2 times 3. So we got 2 times 3 times 5. So this is going to equal log of 2 plus log of 3 plus log of 5. So we have f plus g plus h as our final answer. All right, let's move on to the next section of changing bases, which is really a skill you use when you're using a calculator. So if you want to put in and find out what the number is here, 8 to what power equals 11, in a calculator, you would type in log of 11 divided by log of 8. Right? And we can choose any base we want and still get the same exact number. So in this case, they want us to change it to base 5. If I don't write a base at all, it's considered base 10. But if you want to experiment with it, try just doing log of 11 divided by log of 8, write down the decimal, and then try what this is, find out what log of 11 base 5 is, divide by log of 8 base 5, and you'll find out it is the same decimal. Right, and it just says to change to the certain base, so we don't really need to find out what the decimal is for this answer. That will be acceptable right there. Number 8, change it to base 10, so this is the one where we don't really have to write a base at all. Without writing a base, it's assumed to be base 10. So we'll have log of 2 divided by log of 7, okay, and that's it. If you did write the 10 down here, it wouldn't be wrong, but it'd be kind of like writing, if your answer was x, it's kind of like writing 1x instead, which we don't really need there, so it's not necessary to put the 10. And lastly, we have base e, so we're going to rewrite this as log of 13 divided by log of 3. Right? And these are going to be base e. And when we have a log that's base e, we have a special notation for it. It's called natural log. So we want to rewrite this as natural log of 13 divided by natural log of 3. So always replace log base e with natural logs. All right. Next, let's solve some basic equations here that have like bases. So there's two types of equations that we're going to look at here. Those that have like bases, so these both have 2, And then like on number 11, 27 could be rewritten as a base of 3 because that's 3 to the negative 3, right? And then kind of preview this. If we looked on the back, these questions here that you have to solve, but you can't write this number in the same base, so that's when we're going to get decimals. So some of them you can, some of them you can't. So the ones we're doing right now and how we're going to do them only work when they have the same base. Can't do this on every problem. So they have the same base, and we're trying to get these to be equal to each other. So it makes sense that if the bases are equal, we just need the exponents to also be equal. So we need 3x minus 1 to equal 8. So we just have a linear equation that we have to solve. We're very familiar with. So 3 times what is 9, and x equals 3. And the nice thing about these is you can always check your answer. Plug in 3, you'll get 3 times 3 is 9. 9 minus 1 is 8. So they are equal to each other. Same idea here. We just have to know how to rewrite 27 in the same base. So since we have a base of 3 on the left, how can you rewrite 27 as 3 to some power? So if 3 to the 3 power is 27, that means 3 to the negative 3 power is 1 over 27. So the fraction, remember, are negative exponents. And then we'll do the same thing we just did on the last. Bases are equal, therefore the exponents are. So what plus 1 equals negative 3? Subtract 1 on both sides and you get negative 4. And you can also do a check here. Lastly, rewrite 32 as in the base of 2. So 2 to what power is 32? And if you need to, off to the side, you can kind of start multiplying them. 2 times 2 is 4, times 2 is 8, 8 times 2 is 16, 16 times 2 is 32. So it's going to be 2 to the 5th power. So, like before, bases are equal, therefore the exponents are as well, and we can solve this. Subtract 1 on both sides, divide both sides by 2, and there's our answer. And we can do a check here just to verify if we need to. Okay. Next, let's rewrite these in logarithm form. So remember, the answer to a logarithm is the exponent. So it's a good place to start off is that whatever you write, we're going to have a log here, but the answer is going to equal the exponent, right? And we know the exponent is always attached to a base. So that means this is going to be base 10. That's the small number here, which leaves this other number as a quantity that goes here. Now we technically don't have to write base 10. You could just write it as log of 10,000 because it's assumed to be base 10 if we don't write anything. So this is basically asking 10 to what power equals 10,000, and that would be to the 4th power. Same thing here. The answer is the exponent, so I know I'm going to have log. It's going to equal my exponent, negative 3. The base of negative 3 here is 2, so that's the base of my log. So that must mean this is 1/8. So 2 to what power equals 1 over 8? That would be negative 3. Okay. Lastly, same idea, just with variables. So answer is the exponent, k. The base of k is j, so that's the base of the log. That leaves h to go right here. Now let's do the other direction, convert logarithms into exponents. So this is saying The base is 2. The answer to the logarithm is an exponent, so 2 to the 10 equals 1024. And you can verify these on a calculator. Type in 2 to the 10th power and you'll see that it equals 1024. Same thing here. Answer is an exponent. Base is 81, so 81 to the 1/2 equals 9. Right? And 1/2 power is the same as square root, so the square root of 81 is 9, so that makes sense. Lastly, just with variables, answer is the exponent. Here's our base, so we have b to the v will equal w. Alright, let's move on to the next section, number 19, where we actually have to evaluate and find the answers. Now this is without calculator, so we have to know and understand what the question is asking, and then expect the answers to be some whole answers, no decimals here. So log of 4 base 4. Now if you need to also, you can rewrite this, right, in the exponent format that we just went over. Right? You can convert it to this if that helps. So this is saying 4 to what power equals 4. Right? And if this is easier to understand, think about it and rewrite it this way, and then eventually you won't need to rewrite it anymore, and you'll just look at this and say, okay, this small number to what power equals this bigger number. So 4 to the first power equals 4, so that's why the answer would just be 1. 4 to the 1 equals 4. Same thing here. 3 to what power equals 1? You might remember there was a property that said, well, it didn't matter what the base was. If this number here is 1, there's only one way to get an answer of 1 when you're using exponents, and that's to raise it to the 0 power. Any number to the 0 power is 1. So you can almost ignore whatever this number is, and if you see a 1 here, you already know it's going to be 0. That's always the case. Same thing here. 6 to what power is 6 to the 8th power? So 6 to what power equals 6 to the 8th power? Makes sense that the answer is 8. 6 to the 8th power is equal to 6 to the 8th power. Right. Here we might have to rewrite the problem a little bit. So 5 to what power is 1 over 125? Now the trick here is to recognize that 125 is 5 to the 3rd power. If you know that much, we can rewrite this as log 5 to the 3rd. But remember, this is a fraction, 1 over 125, so that would be negative 3rd. So this is like the last one we did, when we have an exponent, like right here. We can just get an answer, well, whatever that exponent is, will be our answer. We can use the properties we did before as well, just to show the work. Bring down that exponent, and then this is asking 5 to what power is 5, so that would be 1. So that's how we get an answer of just negative 3. But it's fine if you just write negative 3. It's not required to show this, but that's why it works, using the properties from before. All right, right here we have, so 23, there's a couple ways of doing it. One way is to just convert it to the exponential form. So ask yourself, 8 to what power equals 4? Right? And you probably recognize that these are both powers of 2. 8 is 2 to the 3rd power, right? And 4 is 2 to the 2nd power. So we can turn this into a problem by changing it to exponential form, and the same way we did up here, we just changed these to exponent forms. And then solve the equation, since the bases are the same, make the exponents the same. 3 times what equals 2, and then divide both sides by 3. So it's okay to have a fraction answer, but just make sure you do leave your answer as a fraction. It would not be, you don't want to put 0.6 repeating or anything like that. Right, same thing right here, 1/10. Okay, we can rewrite 1/10 kind of like we did in the first problems as a fraction. Right, so 10 to what power equals 1/10. And just have to remember, well, since we're dividing and we get a fraction, that's going to be 10 to the -1 power. So here we'll have x equals -1. Go. All right, next let's look at, do some solving. And this first problem is very similar to the first solving problem we did here. They had the same base, so we just made the exponents equal to each other. Well, on number 10. So on number 25, they have the same logarithm. They both have a log of 2 on both sides, so we just set the other parts here inside equal to each other. So think of number 10 and number 25 as being kind of the same type of problem. We have the same, whether it's an exponent or a logarithm on the same side or on different sides, we can just cancel them out, so to speak, and then solve whatever's left over. So we'll have 35 is 5 times what? And then you'll get an answer of 7. The next one, you'll notice, does not have a log on both sides. So it's a different type of problem, and it's important to realize that, so that way you don't just get rid of the logs and start solving an equation. We can't get rid of it unless it's the same on both sides. So this is asking what number, our base, to the second power is 1/36. So what times itself basically is 1/36. So you can do this a couple ways. One is to take the square root of both sides. Right? That's going to give us a plus or minus x equals 1/6. So that means x could be 1/6 or -1/6. But you might recall that with logarithms, it doesn't make sense to have a negative base. So we actually don't include a -1/6 in this answer. So just positive 1/6 would be our answer. Okay, let's go on to the back. Starting at number 27, you can see we're adding logarithms together. So it might be useful to go back up or go back to the other side and remind ourselves about this. If we're adding logarithms, like log 2 plus log 5 is the same as log 2 times 5, right? So we're going to actually use the same property here, but in reverse. Here we're taking a number, breaking it apart into two parts, and on number 27, we're starting with the two parts that are adding, so we're going to multiply them together. So looking here, see the fact that they're the same base, right? Both log 2 means I can rewrite this as log of x times x plus 2 equals 3. And then, since I only have log on one side, convert this to the exponential format. So 2 to the third power will equal x times x plus 2. And then go ahead and solve this. So we have 2 to the third is 8. Distribute the x, so x times x is x squared. This is a quadratic. X times 2 is 2x. Since it's a quadratic, get it equal to 0. So subtract 8 on both sides. X squared plus 2x minus 8. And then go ahead and solve this using any method. Factoring is probably the fastest. So what multiplies to negative 8 and adds to 2? That'll be 4 and 2, with 4 being positive, x being negative, or 2 being negative, because 4 minus 2 is positive 2, which means our two answers are going to be negative 4 and then positive 2. Now, just like before, check these to see if any of them don't make sense in our actual answer. So if you plug in, let's say, negative 4 right here, well, you can't get an answer that's negative with logarithms. So we have to exclude the negative 4 answer. So we only have one answer, and that is x equals 2. Okay, number 28, same idea. Already have one log, so we can just rewrite this in exponential format. 4 to the third power is what number minus 2? And 4 to the third would be 64, which means x is 66. All right, the next section is the calculator section, where we're going to solve some equations here, but it's definitely going to be a decimal answer, and we're going to round it to the nearest hundredth. I can tell it's a decimal answer because 5 to the second power equals 25, right? And 5 to the third power is 125. So we're trying to get 5 to what power is 30. We know it's going to be a little bit bigger than 2, maybe 2.1 or something like that. And the way to do this is where we introduced take the log of both sides, or convert it to logarithm format. So two ways of doing this. If I convert this to the logarithm format, remember the answer is x, base is 5, so log base 5 of 30. Right? Same question. 5 to what power is 30? And then in your calculator, you can use the change of base and just type in log of 30 divided by log of 5. Okay, and that will be a decimal that will round to the nearest hundredth. So we'll have 30 divided by log of 5. And round this to the nearest hundredth is tenths. Hundredths is right here. So the 3 will keep this at a 1. So this will be 2.11, 2 and 11 hundredths, approximately. And we could double check that just to make sure. It's an equation. So, and since you have a calculator already out, go ahead and check it. Put in 5 to the 2.11 power, and it should be close to, not exactly, but it should be close to 30. So 5 to the 2.11 power is something that's very close to 30. So we know we're in the right area here. Let's go try another one. So convert this to the logarithm format. The answer is the exponent. I know this is going to equal 2x. The base is 3. I'll have 100. Use the change of base, so we'll have log of 100 divided by log of 3 equal to 2 times x, and then we can divide that by 2, and that will give us our answer for x. So first, find out what this is. So we have log of 100 divided by log of 3. There we go. And then take that answer and divide it by 2. So, and round this to the nearest hundredth. So we'll have, look, this is the hundredth place. The 5 will round this up, which will then make us go up to 2.10. Of course, we can double check just to make sure that when we plug in 3 to the 2 times 2.1 power, it should be something close to 100. So 3 to the 2 times 2.1 power is something really close to 100. So we know we're good. Okay. Do a few more. Here we have multiplying by 5 in front of our base and our exponent. So everything we've solved up to this point didn't have this coefficient in front of our base. So let's just get rid of it, and then we can solve this the same way we solved the other ones. So we have 22 over 5 is now going to be 4 to the x minus 2. And then we can do some logarithms to solve this. So our logarithm format would be equal to x minus 2, because x minus 2 is the exponent here. Right? The base is 4. So 22 over 5 goes here. And we can use, we go ahead and add 2 to both sides. We have log of 4 of, or log of 22 over 5 base 4 plus 2 will equal x. Then we just have to use change of base formula here to find out what the answer is. Now, your calculator might have this actual button where you don't have to do this. If you have that kind of calculator, you can use that button as well. So if not, we have to do log of 22 over 5 divided by log of 4. Add 2 to the answer, and that should be our approximation. So log of 22 divided by 5 divided by log of 4, and then add 2. We'll get 3.068, and then rounding the 8 will make this into a 7, so we'll get approximately 3.07. All right, lastly, we have an equation with e, which is a sign that you need to use a natural log as opposed to the log base 10. So we have a minus 23. Let's just clear that out. So we have e to the x plus 3 power is equal to 31. And we can rewrite this as, I'll take the natural log of both sides. Natural log and e to some power, so to speak, cancel each other out. We'll have x plus 3 equals natural log of 31, and then just subtract 3 on both sides. So if we want the exact, it'll just be this. Right? If we want the approximation, just use the calculator. So we have natural log of 31 and then minus 3. So we get approximately 0.434 or 0.43. Next, let's go ahead and do some interest. So we have a few formulas that we use for these. When it's compounded annually, we had a formula that looked like this. Basically says what we want to end up with, right? It's going to be equal to what we start with. That's what the little 0 is. It means that's the amount that we're starting with, the principal amount, times 1 plus the rate to the t power, however long you have that rate for. And make sure your rate is always a decimal. Most of the time it's given to you as percent, so you have to convert that. So in this case is that we're going to end up with $10,000. So it's 10,000 equals what we started with, 2,000. And it's raised to the 1 plus 0.04, that's 4%, to the t power. So we're solving this exponential equation where the variable is the exponent, so you need to use logarithms to solve it. So kind of like the problem above that we just worked on here that had a 5 in front of our base. Here we have 2,000 in front of our base, so divide both sides by 2,000. So 10,000 divided by 2,000 is 5, which basically says how long does it take at 4% to have 5 times as much money? To go from 2,000 to $10,000, that means we increase it 5-fold. And we can use just our logarithm know-how here. So base is 1.04. Right? Exponent is t. So then just use change of base formula. So this is going to equal log of 5 divided by log of 1.04. That'll be approximately what the answer is. Go. So log of 5 divided by log of 1.04. We get approximately 41 years. So that's a long time. Mainly because we're trying to, well, to get 5 times as much money, it's going to take a little while, but then this interest rate, 4%, is very low. Investing wise, you want to have at least 8%. Really good would be 12 to 15%. So if you're getting 4%, that'd be a very low interest rate. So it's going to take a lot longer. Next one, we have compounding continuously. So this right here is the indicator that you need to use the other formula that has E. Continuous compounding uses E as opposed to just the regular rate. So the setup is the same. We ended up with $750, started with 500. That's what the P0 is. That's the starting principal amount. E, and it's asking, well, we're trying to find the rate here. Don't know what the rate is, but the time is 10 years. 10 years. So that'd be 10 times R, where t is 10 and r just stays the same. So we need to solve this equation. Like the last one, divide both sides by 500. And we'll get, let's see here, 750 divided by 500. We get 1.5. So how long does it take to get 1.5 times the money you started with? And since we have an e here, we have to use the natural log. So we're going to have the natural log of both sides. And we have natural log of e will actually be 1, so we end up with natural log of 1.5 equals whatever the exponent is. In this case, it's 10 times r, and divide both sides by 10. So 1.5, natural log of 1.5 divided by 10 equals 0.04. Now, this number right here, since it's an interest rate, should be somewhere between 0 and 1. An interest rate can't be negative. An interest rate cannot be more than 100%. So if you ever get a number that's way too big or way too small, or like it's negative, you'll know something is wrong. But the fact that we got 0.04, which is the same as 4%, makes it likely that's correct. All right. Lastly, let's do a little graphing. And it helps to know the parent graph that you're working with. So in this case, we're working with 2 to the x power. Right? So powers of 2. So think about powers of 2. So if we were doing a chart here, right? So 2 to the 0 power would equal 1. And 2 to the 1 power, to the first power is 2. 2 to the second power is 4. So this gives you a good starting place for graphing this. But we have this x minus 3, not just x, but x minus 3. Recall if it's attached to the x variable, it's going to move it left and right, translate it left and right. So minus 3 translates it to the right 3 places. And then we have this minus 4, which will translate it down 4 places. So we're actually going to take this graph, I want to graph it right here. It looks like this, and we're going to translate it to the right 3 and then down 4, each of those points. So to the right 3 be 1, 2, 3, down 4, 1, 2, 3, 4. Same thing here, to the right 3, 1, 2, 3, and down 4. And since we have a little more space above here, we could actually do another one if we wanted to. And this would be up 4 more. This is like the 3, 8. And we could also look at the negative exponents, right? That's how you get those fractions. So when we did this, just recall that once you get into negative territory, it just starts getting smaller and smaller and smaller, but it's impossible to get an answer of 0. So it never goes below this line on the regular function. So we'll just have the same thing happening here. It just won't get below negative 4. So we'll have our graph function that will look like this. So we have an asymptote horizontal at negative 4. All our graph has to be above that number. It does ask for the asymptote. So again, the asymptote here would be negative 4. And the domain and range. Domain's going to be any number. We can plug in any number into here. So the domain will be all reals. So we can raise a number to any power. Positive, negative, 0. Does not matter. So domain's all reals. You can also look at the graph and you can see, well, the graph will keep going left and right forever and ever. That's another way of getting the domain. The range, however, is limited. We have that asymptote, so the graph is always above this value. It's always above negative 4. So the range is going to be greater than -4. Not greater than equal to, because it can never actually equal that -4. Just like on the parent graph, it can never actually equal 0. And some prefer to write the range this way, and that's fine as well. Either way is fine. So now let's graph the logarithm. So it's going to look very similar to an exponential graph, but it's going to be rotated. Right, so we have a parent graph that would usually starts at an asymptote of 0, right? But in this case, we have a +5, so it's going to be translated 5 to the left. So we're going to look at 1, 2, 3, 4, -5 here for our asymptote. And the graph is also moved down 2. So instead of starting just right here at 0, 1, right, we're going to go down 2 as well. And this is base 3, so the next point is going to be 3 from the asymptote here. It's going to be 3 away. But we also have a vertical stretch of 2. So there's a lot of things going on here that will, instead of going up 1 for the next point, we have to go up 2. And then it's going to be 3 away, same as the base, from that vertical asymptote. And if you want to look at it just as an exponential function on the side, you can think like, well, this is 3 to the 0 is 1, 3 to the 1 is 3, so this is 3 away. 3 to the 2 will be 9. So we'll actually have another point. See, this is 3, so 4, 5, 6, 7, 8, 9. We'll have a third point right there. And then our asymptote will be right here, so this is where all those fractions happen. Never actually crosses the line, but keeps going down forever. We just do our best to draw this curve. There we go. So in this case, we have a vertical asymptote, right? Vertical asymptote is at -5, or at x equals -5. Here, the range, just kind of flip for exponentials, the range, this could keep going down forever, this could keep going up forever. So the range is all reals, whereas the domain is what's limited. The domain starts here at -5 and is completely to the right of it. So it's starting at -5 and goes to the right. So x must be greater than -5. Or you could say -5 to infinity. Either format's fine. Okay, so that concludes the review. Make sure you can do each problem on your own by yourself with no help. There's a lot of little steps, so it doesn't hurt to practice these problems as well as previous problems, especially for these word problems. Practice those on the old assignment and make sure you can do each of those on your own. And good luck.